Thanks, sorry about that. So I'm Brian Carroll from Fetch Robotics, and I'm going to be talking about deterministic message-driven execution with ROS. So to kind of motivate this, I want to talk a little bit about determinism. I think most people are familiar with the term. Deterministic program would be one that would take a given set of inputs and produce the same outputs every time they're pumped in. To give us a little more context in robotics, maybe we want to play back some data we've recorded with a bag, and then we want to make sure that we get the same data out from our software every time that we run it through. And why do we care about this? For the most part, we care about it for having some robustness to timing variations in our system, but at least at Fetch, and I think a lot of other places, it's also good to have some incident reproducibility. I'll talk about this in a bit. So to fully qualify here, when I'm talking about determinism, I mean only algorithmic determinism, kind of at the highest level, not so much real-time determinism in terms of timing. So this would be more in the context of a higher level system, not really the safety critical level. And so we're usually dealing with software that's somewhat low frequency, nothing like a high rate control loop at a couple of kilohertz. That's tolerant to delay and some amount of command jitter. And we're also assuming here that the host system is going to be able to run fast enough to keep up with our messaging. So here's sort of like a hypothetical system that should look familiar to most people. We got a bunch of nodes kind of running in a continuous fashion. We're piping in some sensor information and then creating control inputs for our robot system. And now let's look at one of these nodes sort of at under a microscope. The first kind of example I'm giving here is a node that is timing dependent, so I'll call it the polling ROS node. So in this node, we have a bunch of inputs. We're collecting them via message callbacks, and then we are saving these messages inside of our encapsulating class maybe every time we get a callback to keep the callbacks light. And then in a separate update loop, possibly in a timer or maybe in even another message callback, we're going to check to see if these messages are there, and if they are, we're going to do something with them. So it looks something like this. We get some messages in on our inputs. And then sort of decoupled from that, we run our update callback. And what we end up with is this lack of execution dependence on one another. We end up sampling the inputs that we have. And so our outputs are very dependent on the order in which our messages come in, sort of the timing in which they came in. And what's sort of good about a program that's set up in this way is that it can kind of effectively have zero delay because it's kind of running on its own clock whenever, besides maybe waiting on things that are polling or blocking like TF. But you can't really run faster than real time or even at the same speed and kind of guarantee that your results will always be the same. So to rectify this, we can convert this node into I call it an event-driven ROS node, where we're going to collect all of our inputs from callbacks, maybe double buffer it, and then use some kind of a synchronization policy to look at what messages we have in those buffers and execute accordingly when everything is ready. So here we get some messages, and we run all of our our update when we have a full synchronization frame. And so right now you can use something like message filters to get this to happen in ROS. Typically people use it for synchronizing things like sensor data and transforms. At Fetch we've kind of implemented our own system, which I'm going to go into a little bit later, mostly to extend the specificity of the types of synchronization policies and get some multi-message capture. So what's good about having an event-driven node is that we can be robust to timing variations and some message interleaving at the expense of some delay, so we can wait for some messages to come in and then process them if our system is tolerant of that. The downside being that we incur a delay at every node that's going to be passed on to every downstream node. But the overwhelming positive here is that if we can create these pieces of software that are not timing dependent, we can get repeatability out of functional tests, and we can decouple sort of the effects of our timing on the actual functional input-output relationship of our code. As sort of an extension of this, we can run code fast in real time. Let's say we have a bunch of simulations set up. We want to maybe randomize our system state or some sensor data, and then run a bunch of simulations at once. This is really the only way to be able to do this effectively. And so very specific to fetch, a lot of what we deal with in terms of data back from the field, we get it back in the form of bag files. So we record this data and we get it back, and it might represent kind of an incident that uncovered an edge case in our code. A light example would be something like a robot was stuck by an obstacle for too long, or we missed tracking something that might have been important. And so to get over these edge cases, we could create a test from the bag file itself, just isolating a few pieces of the system that might be important. But again, really the only way to do this is so that we have to make sure that these nodes are going to be repeatably producing the same outputs on these same input pieces of data. And so to answer this question, so it's sort of the manifestation of the system that we use is called, we've called it Flow. It's a framework that is, the backbone is driven by a kind of event-driven, message-driven system. And there are a couple other pieces that are not so related to the event-driven nature of the software. There are a couple of extra supporting features and glue that I'm going to talk about just to give a little bit of context. The idea with Flow is to be able to maintain the node ROS, the ROS node-based structure, but mostly to decouple the execution portion of our code and the communication portion and the ROS transport layer, so we can kind of change that out a little easier. We also want to be able to support intra and extra node communication, so something like something akin to nodelets. And we call these the units that are running in our system blocks. Again, they're very similar to nodelets in that they can be run within the same, several can be run within the same program, but we exclusively run each block in a separate thread. So in the diagram here, we have our ROS transport layers on the end, and on the inside we have these things we call input channels, which are essentially a buffer that the messages get pumped into, and they serve two purposes, one of which is to actually buffer the messages and reorder them in time. And they also come along with a synchronization policy, which sort of defines the synchronization behavior that is going to happen before we execute our event callback. And so a program could look something like this with several blocks that are connected sort of in an intra-block pattern. We've designed in such a way that you don't actually need to use ROS messages when you're passing things within the node. So to get into more of the details about the synchronization behavior, which I think is probably the more important part. So the way it's designed is that we have a bunch of channels, again, like I said, each with a synchronization policy, which defines the overall policy of the event execution. The first input channel, we call it the driving input channel because we use it to produce a stamp or sequence number that is used to synchronize the remaining channels. So on top of besides the synchronization policy, the channels also have the ability to marshal kind of a data discarding, or they can also tell the synchronizer when to dump a frame if synchronization is not possible. So inside of the message buffer portion of the input channel, this is really up to implementation. It's a little bit more flexible, but the way that we have it set up is that there's a buffer which orders messages in time. Right now we're using the message stamp of our ROS messages, but again, it could be any data type, so as long as there's some sort of time backing or a sequence backing to it, you can shove these into the message buffer. And then the more important part is the synchronization policy. So the way that this works is first our driving input channel is going to be waiting for messages, and on getting a new message, the thread that it's inside will wake up, and it will check to see if, against some ready policy, whether or not it should continue. It captures a message and then produces a timestamp or a sequence number that the other input channels are going to use to synchronize against. And then a following input channel is going to get this sequence data, and then it will take in messages, and when it's ready and the messages satisfy the synchronization policy that it has, then it will continue to chain down until we have all of our data, and we'll create this data frame, which will then pass to our execution callback. And now we have all the data we need to run, and then we'll produce an output that corresponds to the sequence information from our driving input. So to go into some details about actually what these policies kind of look like, for the most part, our driving input policy looks something like a sliding window where we're connected to a single topic from a single source. So we're getting things pretty much in order all the time. And we're pulling off the first n messages, and we're using that as our captured data. And then when we're done with it, we'll dump the oldest message. Some of the more interesting following policies include this one, which we try to find the message before and after our synchronization timestamp. And we use this mainly to do things like transform interpolation. Let's say we have a laser scan coming in with a timestamp and we want to transform it. We can get the transform before and after and then interpolate between given our laser timestamp, and then that lines up nicely. Another policy is a closest before policy. So we'll get the message that is closest before our driving input stamp with some delay. And then we also assume a rate. So if we could wait for another message that might be closer based on this assumed rate, then the capture, the input channel will do so. And there are a few other following input channel policies, one of which is a latch policy where we'll get a piece of data and then invalidate all data before that, and then hold on to it as long as there isn't any new data. And then kind of an extension of this, which is an activation channel, where we look at the actual data inside that we've captured and then evaluate it on some criteria. And what we can do with this is effectively deactivate a block because it'll be waiting for a message, and it'll now effectively be in a sleep state if the condition is not met. So as a little bit of an extension of this, we can somewhat fake output-driven events by pumping in a periodic clock message in our driving input. So some other thread or another node can be producing this clock message. We'll capture it on our driving input message, and then effectively we'll get outputs at roughly that rate. And now to sort of tie this back into our testing framework. So the biggest idea of this is that we can keep our execution portion of our code pretty much the same. We don't have to do any like extra test harnessing. All that we have to really design is the types of input policies we have and the code itself. And so for tests, we can take message data from a ROS bag on a single topic, pump all of it into our message buffers and just let it run, and then get those outputs in a ROS bag, and then evaluate those outputs based on some ground truth criteria or something like that. And that's how we get around a lot of our edge cases that way. So to summarize here, determinism is a very critical thing in terms of testing and reproducibility, and a good way to get around some edge cases and incidences with ROS bag functional tests. Obviously not as a replacement for tests that actually involve timing information. And so to address this need, we've developed this framework called Flow. The block portion of it is not probably going to be worked on too much outside of our own context, but the message synchronization portion is actually in the process of becoming open source in the future. And that's all. Thank you.
Time for questions. Okay, let me ask the first question. Have you analyzed how the number of nodes that are passing messages affects to your framework? It's important, the number of nodes you have passing messages, it doesn't affect, or?
I mean, as long as the host system can keep up with, n many nodes or n many, as long as the host system can keep up with n many nodes or n many threads, the framework is not limited to the amount that it can pass around.
We have time for more questions? No? So thank you, Brian.